Hmm. Hey everyone, I guess we are live. चलो अपना नहीं स्क्रीन में टाइमर देख लेते हैं. Let me know if you guys can hear me. Let me know if you guys can hear me well. Let's go to the problem section. Please let me know if you guys can hear me, or if you have some problem hearing me properly. Let me know about that as well. Oh, you guys can hear me. Awesome, awesome. Thank you. So yep, we will be doing so. Yes. So we'll be again solving the questions of interview series 60, and I hope that the questions were good. But yeah, like just tell me like how were the questions? How did the contest go? How did you like the questions? Did you like it? Did you not like it? What were the difficulties that you faced? And if there was some wrong test case in some problem or something like that, yeah, just please start from last question. Ravi बोल रहे start from last question. Vamsi Krishna is saying explain in Python please. I didn't do a lot of competitive programming in Python, so I would be more comfortable with C++ plus plus or Java. So yeah, like but yeah, like the Python. See, what my main intention here is to explain you how to solve the question. Writing the code is just a like 10% of it. 90% is like explaining you how the solution works, how to think about the solution and these things. So I believe like if agnostic of language, the logic should be clear to you. And definitely like if you are coding in Python, it should be advantage because you will get to write the code yourself, right? So that is definitely an advantage. uh, First question test cases were tricky. First problem was going for me, three was difficult. Spent time on that problem a lot. Which problem? I'm not sure. Anyways, yep. So let's actually try to solve the problems one by one. So let's start with the first problem. Let's go by the order. And to be very fair with you, I haven't solved the problems myself yet. Like I'll be kind of solving the problems live completely. I might have given a bit of thought, but yeah, like that's like just 10 or 15 minutes before the start of the session. So yeah, like we will try to see like how whether I'm able to solve, like, and if I'm not able to solve, just help me out. If anyone has been able to solve that, I might get stuck as well. So yeah, let's do that, right? So the first question is, given the array of positive and negative integers, you have to make the array beautiful. An array is beautiful if two adjacent integers arri and arri plus 1 have the same sign, right? Okay. If two adjacent integers have same sign, the array is beautiful. You can do the following operation any number of times until the array becomes beautiful. If two adjacent integers have different signs, remove them. Got it. Return the beautiful array after performing the above operation. An empty array is also a beautiful array. Okay, there can be many adjacent integers with different signs, so remove the adjacent integer with different signs from left to right. So it is also telling you how would you do the operation, right? It is telling you that remove adjacent integers with different signs from left to right. So you cannot, like, let's say here 2 minus 2 is there, you cannot remove minus 2 and minus 2 and 1. These are also of different sign, right? But you will be removing 2 minus 2 because you will always remove from left to right. Okay. So uh, it's okay, Joy. I might not be able to solve the first problem myself, so don't worry about that. But we'll try to figure it out together, right? So let's try to figure it out together. So we are, what is the question again? We are given an array of integers. Some integers are positive, some integers are negative. You have to convert the array into a beautiful array. What is a beautiful array? All the integers will have same sign, like consecutive integers will have same sign. That actually brings us to a very easy observation that all the integers will have to be of the same sign in the beautiful array, right? All the integers has to be positive or has to be negative, because if there is a mixture of positive and negative, at least two elements will be there which are adjacent and have different signs, so they should be removed, and eventually like we'll end up with only a subset of the array which is like entirely positive or negative. So that is a very clear observation that we can draw, that hey, the final array should be either positive or negative completely, right? Yes. So 2 minus 2, 1 minus 1. Again, in this case, see, this is interesting. 2 minus 2. Again, you will be removing from left to right, right? So you can remove minus 2 and 1 as well, but you will always remove from left to right. So 2 minus 2 will be removed. So you go to 1. 1 minus 1, again, that will also be removed. So that's basically how you solve the problem, right? So let's understand the solution. So we have a few positive numbers, right? You have a few okay, I have this ulta. Okay, so you have a few numbers, positive and negative numbers, right? So let's say 5 4 minus 2 3 4 minus 3 2. So and minus 3 minus 2, let's say, right? So what will be the final answer? So let's understand this. So this is kind of similar to, I would not say very similar, but kind of similar to bracket matching, right? Like you can consider the positives as like this and negatives as the opposite way, right? So positive, positive, negative, negative, and basically whatever is the remaining part of the bracket, that is the answer, right? So kind of very similar, you can kind of draw an analogy between bracket matching and this, but although, or ones and zeros, right? Ones and zeros also will work, like positives are ones, negatives are zero. You have to form an array of ones or zeros. Two consecutive 1 and 0 will be, or 2 1 0 which are consecutive to each other will be removed. So that's what you have to do, right? So how would we do this? We'll take a stack, right? We'll take a stack. So 5, let's insert 5, right? 5 is inserted. So we will insert whenever it's a positive element and remove whenever it's a negative element. So next we have 4. So 4 is inserted into the stack. Next we come to minus 2. Whenever we come to minus 2, see, on the top of the stack there is a positive element, right? So we'll remove that. These two will get removed because 4 and minus 2 will be next to each other, right? So minus 2 is getting removed. So next we go to 3. So 5 is of positive, 3 is also positive. So 3 will be inserted into the stack. Next we have 4. So basically, like, if the stack is empty, the next element will be inserted irrespective of the sign. If the stack is not empty, then you will check the top of the stack. If the sign of both the elements is same, in that case insert, otherwise you will remove, right? So 3 is inserted, 4 is inserted, right? Next we have minus 3, so 4 will be removed, opposite sign. Next we have minus 2, so 3 will be removed, right? 3 will be removed. So 3 will be removed and the final answer will be 5. So eventually 5 will be left, and if you see, that's true. 4 minus 2 will be removed, 4 minus 3 will be removed, 3 minus 2 will be removed. So only 5 will be remaining, and that is the answer, right? So pretty simple question, right? So again, the logic will be, if the stack is empty, right? First is, if the stack is empty, we will insert into the stack. Else, check sign of current element and top of stack. If same sign, insert, else remove, right? So this will be the logic. See, again, like, you can solve it in different ways. You can use something like pointers as well, that will also work. But again, like, stack will help us maintain the history as well. Like 4 here, 3 was to be paired with minus 2, so those things will be a bit tricky. But again, you can definitely, like, use similar things as well, right? You can use pointers as well and get it done. So let's try to write the solution. Stack makes it a much simpler actually. So let's try to get it done. Stack int st for int v belongs to arr. Okay, v belongs to arr. So for v belongs to arr, if st dot size equals to 0, that means the stack is empty. So what we'll do, st dot push v, we'll just push. Else, if the sign is same, right? So if v greater than 0, sorry, if v into st dot top, although I'm assuming it should it will exceed integer limit. All right, let's do something like this, that let's do something like this. V if v, let's write the conditions only. If v greater than equal to 0 and st dot top greater than equal to 0, else if v less than 0, or rather less than equal to 0, and st dot top is less than equal to 0. So in this case, st dot push v, st dot push v. Otherwise, if there are different signs, else st dot pop. So different sign could also be checked by like multiplying them and checking like greater than 0 or less than 0. But again, there might be some typing problem, like we have to convert into long and those things. So that's why I'm just avoiding that. So else is done. Right, st dot pop. And finally we have the elements that are actually important to us. So vectored int answer for int x belongs to for while st dot size greater than 0, answer dot pushback st dot top and st dot pop. So we have the remaining elements, but the remaining elements are to be reversed. So return reverse of answer dot begin and answer dot end. Right. So we'll reverse because the stack will give us the elements in a reversed way, right? So we have to reverse it. So let's compile and run. Reverse is not there. That's interesting. We have to reverse it manually. What is the issue? Could not convert reverse into how does reverse work? Reverse, what is the format? -4 0. It said with dicey to me -4 0. What should happen? Ideally they should not cancel out, because 0 is like, again, like we'll look into the condition. If -4 0, actually we can test it out, right? So let's just test it out. That we'll just take two elements and -2 and 0 and just test if like what's the expected output, and based on that we can just form the condition. -2 0, it's giving us empty. So actually we should, and 2 0 should also give us 2 0 should not give us empty. Then let's see, 2 0 should not give us empty. So 0 is considered to be positive. 2 0 is okay, not empty. So v less than 0 and st top is less than 0. Simple. So negatives will only be considered with negatives and positives will be only considered with positive. Reverse, okay, what was the issue with reverse actually? Oh, मैंने function return कर दिया. अच्छा, reverse doesn't return the array, right? Sorry, my bad. So return answer. मैंने function ही return कर दिया. Reverse is like reverse the array in line. Sorry, in place. Like it will reverse the actual array. It will not create a new array and return that. So that makes sense. Reverse 2 2. Is this correct? I'm not sure. Let's test it out. Expected क्या है? Let's test it out. To submit. Yeah, if you're confused, like if you're ever confused between negatives and positives, right? Like for example, I considered 0 and -2. Again, like you can always you can just always try writing the solution without negative. You'll maximum get one wrong answer, right? And you can just then change the sign and check if this works again. So because these, like again, these should be cleared in the question, but in case they are not, you should always like take some guess. Like it's a kind of obvious guess that 0 is kind of positive, right? So you can just take that guess and go ahead. Chalo, let's go to number of good components now. So number of good components is given a undirected graph with v vertices numbered from 1 to v and e edges. find the number of good components in the graph, right? So a component in the graph is good component if and only if the component is a fully connected component. A fully connected component is a subgraph of the given graph such that there is an edge between every pair of vertices in the component. Kindly explain this again. Last one. चलो फिर से क्विकली एक्सप्लेन कर लेते हैं. सो बेसिकली आई थिंक द क्वेश्चन इज क्लियर, राइट, कि इफ देर आर लाइक इफ टू कंसेक्यूटिव एलिमेंट्स आर ऑफ डिफरेंट साइन दे हैव टू बी रिमूव्ड, यू विल डू दैट ऑपरेशन लेफ्ट टू राइट. व्हाट इज द रिमेनिंग सेट दैट यू हैव टू रिटर्न, राइट? Now like one thing to note here, that after this the observation that follows is all the elements will either be positive or negative, but we'll just do a brute force way, like we'll just remove elements whatever is asked in the question. We'll go through the elements one by one. If two elements consecutive are negative, we'll just remove them. But there is a tricky part here. Just consider this case of 5 4 minus 2 3 4 minus 3 minus 2. यहाँ पर 4 and minus 3 are paired together, but then 3 and minus 2 will also be paired together. So we are kind of drew an analogy between the positives to be like opening brackets and the negatives to be closing brackets, or the vice versa as well. And whenever the opposite sign comes in, we'll just remove them, right? And whatever is remaining, like we'll be basically doing a bracket matching. So 4 minus 2, so when 4 comes in, 4 minus 2 are mapped, like when minus 2 comes in, minus 2 and 4 are mapped together. Then 3 comes in, 3 is pushed into the stack. Then 4 comes in, 4 is pushed into the stack. Then minus 3 comes in, minus 3, we see that the top of the stack has a different sign, so 4 and minus 3 are popped together, right? 4 and minus 3 will be popped together. Now what is at the top of the stack? 3, so 3 and minus 2 will be kind of paired together, right? So they will be popped together, so kind of like this. So we are maintaining a stack. If it is empty, you will insert. Otherwise, you will check the sign of the top of the stack and the current element. If it is same, then you can insert. Otherwise, you will remove the top of the stack. That's the solution. Minus 3 minus 1 ठीक है, कर लेते हैं. चलो minus 3 minus 1 minus 19 0 6 minus 13 12. So what we should do, we'll maintain a stack. Now it is empty, we will push minus 3. Then we have minus 1, same sign, will push. Minus 19, same sign as the top of the stack, so minus 19 is pushed. After that 0, 0 has a different sign, 0 is positive here, so minus 19 and 0 are paired together and removed. After that 6 comes in, 6 and minus 1, different sign, so minus 1 is removed and they are paired together. Minus 13 comes in, same sign, so minus 13 is inserted. 12 comes in, minus 13, 12 different signs, so they are paired together and removed. So minus 3 is the final answer. Utkarsh, is this clear? Minus 3, how is it coming minus 3? Okay, awesome. Chalo, let's go to the next question quickly. Again, like we have the question is, again I'll describe briefly. We have a graph. The graph is not fully connected, right? So there can be multiple connected components of the graph. We have to find how many good components are there in the graph, how many good connected components are there. What is a good component? A good component is a component in which all the vertices are connected to each other. Like it is a component which is fully connected. It is a fully connected subgraph, right? It is a fully connected subgraph. So for example, this one 1 3 2, it is a fully connected subgraph, right? So the output will be 1 and there is only one connected component and it is fully connected. All the vertices are connected to each other. 1 3 2 4, there is one connected component and not all the vertices are connected to each other, so the output is 0. So it tells you for every connected component, right? It doesn't mean that you have to find a connected component or find a subgraph that is fully connected. Rather, it tells you for every connected component, see if it is fully connected. So there is only one connected component here, right? This entire thing, is it fully connected? No, it is not fully connected. So this is the the output for this will be 0. So this is basically the question. Now we have to find the number of good connected components. The constraints are given to us, and any other thing that's relevant, I don't think any other thing is given to us. I'm just worried about self edges and repeated edges, but I think let's first assume that there are no self edges and repeated edges, and after that we can like see if it doesn't work, like we can go ahead with adding the conditions, or we can add the conditions as well, like for self edges and repeated edges, right? Okay, sure, I'll zoom in a bit. So let's understand how do we solve this. So we are asked, now the question is clear, right? For every connected component, so for every connected component we'll do something, right? For every connected component, we have to see if it is fully connected. If it is fully connected, as simple as that. So we'll go through all the connected components and we'll see if it is fully connected or not. What do we mean by fully connected? Means there is a edge between every two vertices of that component. Let's say 1 2 3 4, right? 1 2 3 4. This will make it fully connected. Now see, this makes it fully connected. That is, 1 is connected to 2 3 4, 2 is connected to 1 4 3, 3 is connected to 1 2 4, 4 is connected to 1 2 3. So it is now fully connected. What is the condition for a graph? Provided there are no self edges, self edges means 1 is connected to 1, like this. There are no self edges and there is no repeated edges, right? Repeated edges means there is no edge between 4 to 2 times, right? Only one time it is there. Provided these two conditions are satisfied, what is the condition for a graph to be fully connected? The condition for a graph to be fully connected is that the degree of every vertex v, is equals to number of nodes minus 1. Number of nodes in the connected component. So number of nodes in connected component minus 1. That is C. Degree means what? How many edges are going out, or how many edges are connecting that node. So for every node, see, the number of connected degree of that node is number of connected component minus 1. That is the number of edges that the node has minus 1, right? Out degree, here out degree, in degree are the same thing because it's a undirected graph. So number of edges going out from that node, or degree of that node, should be connected components minus 1. So here see, 1 has components, size of connected components is 4. So 4 minus 1, that is 3. So 1 has 3, 2 has 3, 3 has 3, 4 has 3, right? So all of them has 3. So that's why it is fully connected. So what will be the logic for us? For every connected component, first of all we have to see how many nodes are there, right? We have to first count the nodes. So the logic for us will be, first count the nodes of a connected component. Also maybe store the nodes somewhere. And if you store the nodes for the connected component, you can get the size by doing a dot size, right? So store the nodes for every node. Calculate degree. How do you calculate degree? It's pretty simple, right? The adjacency list size. So let's say we want to calculate the degree of V. What is degree of V? The adjacency list size. That is the degree, that many nodes it is connected to. This is the degree, right? This is the degree, right? यार मैं कहाँ आ गया, ये तो कुछ और ही खुल गया, रुको। रुको मेरा यार बता दो एक बार, इफ आई एम लाइव और नॉट। हाँ, ओके, यस, right? So adjacency v dot size, that should be the degree of a node. So it's pretty simple, right? We have to do a DFS. In the DFS we'll see how many nodes are there in the current connected component. We'll store these nodes. Now for every node we will see if it's equal to the if the degree of each node is equals to the number of nodes minus 1. And degree, how do we find? We can find from the adjacency list, provided we are sure, we know that the adjacency list doesn't contain any self edges and repeated edges. So let's assume that for now and write the code, and then if it gives a wrong answer, we'll see. Like if it actually, we have to tackle that, right? So unnecessarily, my net is not working properly. Yes, I am also understanding like my net is causing some problem. But let me know if you can hear me now. Let me know if you can hear me now. Is it better now? Only then I'll proceed. Is it better now? I'll zoom a little. Don't worry about that. I'll zoom a little. Low. Okay. So let's try to write the code for this. So let's maintain the vector int nodes. That will maintain the nodes of the current connected component, and also let's maintain a visited array, right? For the nodes that are visited. So visited. And void dfs int s. If visited is equals to true, and nodes dot pushback s. For int v belongs to g of s. We need the adjacency list as well. So let's say we are passing this, or let's just store it here only, right? Vector int g. We'll just copy this with adjacency list g, the graph, right? So g of s, if not visited v, dfs v, and that should be the dfs code. That should be the dfs code, right? So let's do this. So g equals to adjacency. First of all, copy visited equals to vector bool v plus 1 false. Initially everything is not visited. Let's quickly check if the edges are numbered 1. Okay, edges are numbered from 1. So let's follow that only. V plus 1 false, and for and int answered equals to 0. For int I equals to 0, I less than I equals to 1, I less than equal to v, I plus plus, right? So if not visited I, that means it is a new connected component. We'll do dfs of I. Now once we are done with dfs of I, we'll have the nodes in the nodes. Also we have to clear the nodes every time. So nodes dot clear, right? Nodes dot clear visited of I. And now for int u belonging to nodes, and let's maintain a variable called bool is complete, is completely connected, equals to true initially. Now for int u equals to node, if g of u dot size, also what is this g of u dot size equals to nodes dot size minus 1. Nodes, total number of nodes in the connected component minus 1. If it is not equals to, sorry, if it is not equals to, in that case is completely connected equals to false and break, right? And if is completely connected, answer plus plus, return answer. Yeah, that should be the code. I'm not sure. Yep, I think this should be the code. Let's see if this is running at all. But yeah, we have assumed, like we have made a very big assumption that there are no self edges and there are no repeated edges. But again, if that's the case, we have to tackle those things as well. But yeah, like without that, let's see if this is work. What does the variable node denote? Node denotes the number of the nodes in the current connected component, right? So that's why whenever we are visiting a node in the connected component, we are pushing it to the nodes array. So in the connected component, we'll always visit the nodes, right? All the nodes in the same component. So that's why we are doing this, right? So let's submit this. Yes, this is also working. So yeah, luckily we don't have those things, right? But yeah, like node is, I think node is clear, right? It is the nodes in the connected component. The nodes are basically the nodes in the connected component. So whenever we are seeing that a node is not visited, whenever we are seeing I is not visited, that is we are starting a new connected component. So first thing, we are clearing the nodes array. After that we are calling dfsi, where all the nodes in the current connected component are getting stored, and after that we are going through all the nodes in the component and checking if there is there is any node which is whose degree is not equals to nodes dot size minus 1. Explain the code, sure, I can do that. So see, first of all, again, like let's go line by line. It is the logic is pretty simple. First of all, we are copying g equals to adjacency. Basically g is like what we're using to represent the graph in this, but again that's not needed at all. Visited, we are first of all marking all the nodes as not visited, because we want to find the connected components. How do we find the connected components? Using dfs, right? In a dfs, whichever nodes we are visiting, they are belonging to the same connected component. What is the connected component? Nodes that are connected, right? Nodes that are connected somehow with each other form a connected component. So that's what we are doing. We are going through all the nodes one by one. For every node we are checking if it is visited already. If it is visited, it has already been part of some connected component. If it is not visited, it is starting a new connected component, and we want to explore that connected component, right? So first thing we do is we clear the nodes array. Why? Because for nodes we want to store what are the nodes in the current connected component. So the nodes might be storing some information from the previous connected component. We don't want to push it forward to this one, right? So we want the nodes for this connected component only. So we are clearing the nodes fast. After that we are calling dfs of I. In dfs, what we are doing, we are first of all visiting the node. So we are setting visited s equals to true. Nodes dot pushback is, because in the nodes we want to have all the nodes in the current connected component. So whenever we are visiting a node in the current connected component, and we will visit all the nodes in the current connected component, right? So whenever we are visiting, we are pushing it to the nodes array. After that we are doing the standard dfs, right? Now once we are done with the dfs, what does the nodes array store? It stores all the nodes in the current connected component. What is the condition for this connected component to be a good one? All the nodes should be connected to each other. That is, the degree of each node should be equals to number of nodes minus 1, total number of nodes in this component minus 1. How many nodes are there in this component? That is given by nodes dot size. So nodes dot size minus 1. What is the degree of a given node? So we are going through all the nodes. The degree of the given node is given by g of u dot size, the graph of u dot size, the adjacency list size. If it is not equals to nodes dot size minus 1, is completely connected, is false. That is, it is not connected, and we break. If it is completely connected, answer plus plus, return answer. Is this clear now? We can simply make a vector of vectors, store all the component list. That's what we are doing, right? That's what we are doing. Like, we are not making a vector of vector, rather we are using only one vector and reusing that for every component, nothing else. And this is better, definitely. So yes, as Lucifer said, most of the questions are DFS, BFS only when it comes to graphs, but it's just a minute implementation, like minute modification on DFS and basic DFS, BFS. But yeah, like most of them are. So just think about how you can DFS, how you can BFS, and store, like whenever it's related to distance, right? Whenever you have to see, you have to travel in a level wise fashion, let's say minimum distance or something. If the weights are like same, definitely it's generally BFS, right? Whenever it's related to some distance and weights are like weight is 1, age weights are 1. Whenever it's age weight is there, it's Dijkstra. Whenever otherwise, mostly in most cases it's BFS, it's DFS, right? Be it articulation points, be it bridges, everything needs DFS eventually. So everything is eventually DFS. Anyways, this is the question, this is the solution. Anyone has any doubts? Are these solutions available in Python? Maybe like you can check out the editorials and see if this is available. But yeah, like Python also will be a very similar code to this, not very different, right? So there instead, like you will just maintain self.g, self. That and this, right? Okay, so let's go to the next question without wasting time. Minimum Bst sum sub tree, right? So given a binary tree and a target, find the length of the minimum sub tree with the given sum equal to target, which is also a binary search tree. Okay, so we are given a binary tree and a target. We have to find the length of the minimum subtree with the given sum equals to the target, which is also a binary search tree. Okay, that's interesting. We have to do a lot of things here. Cool. Cool. Okay, let's see. Okay. Okay, so basically what is given to us? We are given a binary tree, right? We are given a binary tree and we have to tell whether like we have to find the minimum subtree whose sum is equals to some target. It is also a binary search tree, so we have to do three things parallelly, right? We have to match the sum of the subtree with the target. We have to check if the subtree is a binary search tree. We also have to find the minimum length. We have to find the size of that subtree as well. So we have to do three things. We have to essentially do three things, right? Okay, we have to essentially do three things. So -1 if there is none with the target. Okay, or it is not a BST. Okay, so implementation wise, it might look length means the number of nodes. The number of nodes in that subtree should be like minimum, right? So for example, in this case 5, 17, 16, if you see this 5, 17, 16, they sum up to 38 and they have a size of 3. There are 3 nodes, right? So, and this is a binary search tree as well. If you see the subtree under 5, it is a binary search tree. Like on the left elements are less, on the right the elements are greater, right? For 17 also, on the left the elements are lesser. So it is a binary search tree and the length is 3. So that's why the answer is this one. Can't we assume the subtree will be a BST? No, we cannot, because the given tree is not a binary search tree. The given tree is a binary tree. It is not a binary search tree. It is a binary tree, right? So we have to ensure that the subtree is a BST. We have to find the sum of the subtree. We have to find the length of the subtree. These are the three things we have to do. But it's so again, like it might be looking very difficult, but essentially it's pretty simple, right? It's eventually given a node, right? Given a node n, what do you have to ensure? Subtree of n, right? Subtree of n is BST. We have discussed how to check if the subtree of a node is a binary search tree or if a tree is a binary search tree. We have already discussed how to do this. It's pretty simple. You just have to assume that it is, or the left subtree is BST, left subtree is BST, the right subtree is BST, and the minimum value in the left child and the maximum value in the left child is less than the given value here. The minimum value in the right child is greater than the max value at the given node, right? So that is the condition for a node. That is the condition for a node to be a binary search tree, right? So again, what should be the condition for a binary search tree? Given a node, it is a BST if the minimum of the left subtree is a binary search tree, the right subtree is a binary search tree, the maximum of the left subtree is less than the given value v, the maximum here max, the minimum in the right subtree is less than, so max is less than v less than minimum. This should be the condition. Then the given node is अरे भाई क्या बताया इसने. You do not have to make the entire tree to be a binary search tree. तुमको पूरा ट्री को बाइनरी सर्च ट्री नहीं करना है. तुमको बताना है एक मिनिमम सब ट्री, एक सब ट्री जो बाइनरी सर्च ट्री है उसका सम इज इक्वल्स टू द टारगेट भी है. तो इफ यू लुक इनटू दिस 5, 17, 16, you will see it is a binary search tree. 5 is a 5 is a binary search tree because 5 के राइट में 17 है which is greater than 5, 17 के लेफ्ट में 16 है which is less than 17 but greater than 5. So it is a binary search tree. The sum of this subtree is 38, so the answer will be 3. The length of this, you have to find the minimum length. ठीक है, you have to find the minimum length. तो ये बन गया अपना कंडीशन सब ट्री ऑफ n. हाउ टू सी if n is a BST. Second is you have to find the sum of the subtree. Sum of subtree of n, that is pretty simple. It's basically the summation of all the child nodes, summation of subtrees of all the child nodes of n plus the value of n, right? Plus the value of n. So that is the summation. Third is number of nodes in the subtree, count of n, let's call it count of n. It is also pretty simple. It's basically count of all the nodes of the subtree plus 1, that is count of n. So this is how we have to, like, for every node we have to calculate all these three things. We have to store them as well, definitely, and then we can see how many nodes are there that are satisfying this condition. So we have to solve each of these independently. We have to solve each of them one by one, find their values, and then finally look into which is the smallest subtree that has the given condition. A subtree consists of one leaf node is a binary tree. Yes, it is a binary search tree. Yes, one node is a binary search tree. ठीक है. So we have to do all these things together. इतना कुछ करना है, फिर क्वेश्चन का सोल्यूशन आएगा, राइट? तो यार पहली बात है, we have to maintain for each node if they are binary search trees, right? So let's maintain it like this. या तो हाँ अभी कर सकते हैं या तो बाद में कर सकते हैं. अभी कर ले क्या? कर सकते हैं मिनिमम. Yeah, पहले we'll compute the subtree size and the sum, right? Node star int subtree size map node star int sum subtree. We'll first do these two things, right? Void DFS node star current. If current equals to null, return int कर लेते हैं इसको, int return 0 कर लेते हैं इधर. अदरवाइज subtree size okay, int total size equals to एक एक करके कर ले सकते हैं, नहीं तो करेंट नल पे आएंगे ही नहीं. चलो करेंट नल पे आएंगे ही नहीं, वॉइड कर लेते हैं. चलो हो गया, वॉइड कर लेते हैं. चलो इफ करेंट ऑफ लेफ्ट इज इक्वल्स टू नल एंड करेंट ऑफ राइट इज इक्वल्स टू नल, दोनों ही नल है तो दिस इज अ लीफ नोड. दोनों ही नल है तो इट इज अ लीफ नोड. प्लीज एक्सप्लेन वाई चाहिए. मैंने वो आते हैं, रुको थोड़ी देर में आते हैं, पहले ये कर लेते हैं, ठीक है? सम ऑफ सबट्री और सबट्री साइज कर लेते हैं पहले. इफ बोथ लेफ्ट एंड राइट सबट्री लाइक चाइल्ड इज नॉट देयर, इन दैट केस सबट्री साइज क्या होगा? सबट्री साइज ऑफ करेंट इज इक्वल्स टू 1, एक हो जाएगा. सम सबट्री कितना होगा? सम सबट्री ऑफ करेंट इज इक्वल्स टू करेंट का जो डेटा है वो बन जाएगा, राइट? करेंट का जो डेटा है वही बन जाएगा, एंड रिटर्न कर दो फिर. एल्स इफ करंट ऑफ एक चाइल्ड नहीं है, लेफ्ट चाइल्ड नहीं है, मान लो करंट ऑफ लेफ्ट इज इक्वल्स टू नल बट राइट चाइल्ड है. राइट चाइल्ड अगर नहीं होता तो पहला कंडीशन सेटिस्फाई हो जाता, तो राइट चाइल्ड तो है. चलो सबट्री साइज ऑफ करंट इक्वल्स टू 1 प्लस, तो पहले डीएफएस करते हैं, आराम से करते हैं. डीएफएस करंट ऑफ राइट, subtree size of current is 1 plus subtree size of current of right. Sum subtree of current equals to current of data plus sum sub tree करंट ऑफ राइट. ठीक है. एल्स इफ मान लो एक चाइल्ड है, राइट चाइल्ड नल है, लेफ्ट चाइल्ड है, तो राइट चाइल्ड इज नल. तो फिर अपना क्या होगा, अपना पूरा ये चीज जो है लिखा है हमने वो पूरा उल्टा हो जाएगा, लेफ्ट के लिए हो जाएगा. तो लेफ्ट चाइल्ड है, राइट चाइल्ड नहीं है. सो इन दैट केस वी विल डीएफएस टू द लेफ्ट चाइल्ड, विल फर्स्ट डीएफएस टू द लेफ्ट चाइल्ड, 1 प्लस सब ट्री साइज ऑफ द लेफ्ट चाइल्ड, देन करंट ऑफ डेटा प्लस 1 प्लस सम सब ट्री ऑफ द लेफ्ट चाइल्ड. लेफ्ट चाइल्ड है, एल्स दोनों चाइल्ड ही है अपने पास, दोनों चाइल्ड ही है. तो फिर एक एक करके डीएफएस करते हैं. लेट्स डू डीएफएस वन बाय वन. डीएफएस करंट ऑफ राइट, डीएफएस करंट ऑफ लेफ्ट, लेफ्ट राइट भी कर सकते हो, सेम थिंग. सब ट्री साइज ऑफ करंट equals to 1 plus subtree size of current of left plus subtree size of current of right. Sum subtree of current equals to current of data plus sum subtree current of left plus sum subtree current of right. Chalo, this what will this do? This is basically finding the subtree size of each of them and the sum subtree of each of them, right? Sum subtree of each of them and the subtree size and the sum subtree, ये दोनों मिल गया. sum subtree का मतलब what is the sum of all the values in the subtree, subtree size what is the number of nodes in a subtree. ये दो चीज मिल गया हम लोग को. चलो पहले डीएफएस करंट कॉल कर लेते हैं, डीएफएस रूट कॉल कर लेते हैं. वी हैव ऑल द वैल्यू स्टोर. चलो सारा वैल्यू हमको मिल गया. अभी कुछ झमेला नहीं है, अभी हमको बस प्रूफ करना है. अभी वी हैव टू जस्ट इंश्योर. नाउ व्हाट वी हैव टू डू, फॉर एवरी सब ट्री वी हैव टू चेक इफ इट इज अ बाइनरी सर्च ट्री, and also we already have the subtree sum, right? So using that subtree sum we can see what is the, if it is equals to target, if it is equals to target we have to check if it is minimum as well. So we have to ensure the subtree size is also minimum, right? तो उसके लिए कुछ कुछ वेरिएबल्स मेंटेन करना पड़ेगा हमको. क्या मेंटेन करना पड़ेगा? आंसर. आंसर क्या होगा? आंसर विल मेंटेन द मिनिमम आंसर दैट वी हैव फाउंड टिल नाउ, राइट? मिनिमम आंसर दैट वी हैव फाउंड टिल नाउ. और क्या मेंटेन करना होगा? और मेंटेन करना होगा, हाँ, और क्या मेंटेन करना होगा? फॉर okay, again let's come back to the condition, right? What makes a tree a binary search tree? What makes a tree a binary search tree? Let's understand this. Let's say given a node n, what will make this tree a binary search tree? What is the condition of binary search tree? All the elements on the left hand side should be given less than n. All the elements on the right hand side should be greater than n, right? That is the condition and that should be true for the entire subtree. Okay, for n, how do we check if n is a binary search tree? Is Bst n? How do we check n is a binary search tree, right? Let's understand this. N is a binary search tree if and only if, let's call the child as L comma R, if is Bst R L and then is Bst R, that is the left child is a binary search tree, the right child is a binary search tree. Also we have to ensure that n actually becomes a binary search tree by combining these two. So n, this entire thing comes on the left hand side of n, right? And property of the binary search tree is all the elements on the left hand side should be less than n. So the maximum element in this subtree, should be less than n. So maximum element in this subtree should be less than n. So and then maximum element on the left subtree should be less than n. Also the right subtree should be completely greater than n. So the minimum element of the right subtree should be greater than n. So this is the condition that makes n a binary search tree. This is the condition that makes n a binary search tree. L should be a binary search tree. R should be a binary search tree. The maximum of this left subtree should be less than n. क्योंकि सारा एलिमेंट छोटा है तो मैक्सिमम छोटा होना पड़ेगा. राइट सबट्री सारा एलिमेंट्स बड़ा है तो मिनिमम बड़ा होना पड़ेगा देन n. So this should be the condition for ensuring that a node is a binary search tree. ठीक है, तो बस यही करना है हमको, मिनिमम एंड मैक्सिमम फॉर द लेफ्ट एंड द राइट सब ट्री मेंटेन करना है, राइट, एंड वी कैन इजीली कंप्यूट आफ्टर दिस। तो कोशिश करते हैं कैसे करना है मिनिमम और मैक्सिमम, इधर ही हम लोग एक्चुअली मेंटेन कर सकते थे व्हाट इज द मिनिमम ऑफ द लेफ्ट सब ट्री, व्हाट इज द मैक्सिमम, इधर भी कर सकते हैं और सेपरेटली भी कर सकते हैं, दैट्स कंप्लीट। लेट्स मेक इट इजियर, राइट, लेट्स जस्ट मेंटेन द, ऐसे ही कर लेते हैं, चलो, नोड स्टार्ट एंड इंट मीन वैल्यू एंड मैप नोड स्टार इंट max value. So min value max value will store what is the minimum element in the subtree, what is the maximum element in the subtree. So in this case if there is one node, so min value of current equals to what, current of data, max value of current equals to current of data, बस उतना ही है। अगर लेफ्ट चाइल्ड है मेरे पास, अगर लेफ्ट चाइल्ड है मेरे पास, तो मीन वैल्यू ऑफ करंट क्या होगा, या तो इट विल बी द मिनिमम ऑफ द करंट ऑफ डेटा, या तो करंट का डेटा जो है वो मिनिमम है, या तो मेरा राइट सब ट्री का वैल्यू जो whatever we have gone from the right sub, whatever we have gotten from the right sub tree, that is the minimum value there, the minimum of them। मैक्स वैल्यू क्या होगा, equals to या तो the current data that we have, that is the maximum, or the max value that we have gotten from the right subtree, that is the maximum, whichever is the maximum। सिमिलरली इधर भी सेम चीज हो जाएगा, बस लेफ्ट को राइट कर दो, लेफ्ट राइट कर दो थोड़ा, रुको कर लेते लेफ्ट राइट, चलो, मीन करंट इज करंट ऑफ लेफ्ट, अभी लेफ्ट चाइल्ड हमारे पास है, तो मिनिमम लेफ्ट का या तो करंट नोड का, जो भी मिनिमम है, मैक्सिमम लेफ्ट का या करंट नोड का, यहां पर हमको दोनों ही अकाउंट करना पड़ेगा, राइट। सो मीन वैल ऑफ करंट इज इक्वल्स टू द मिनिमम ऑफ करंट ऑफ डेटा, मिनिमम ऑफ करंट ऑफ डेटा, या तो मिनिमम ऑफ लेफ्ट का या राइट का, विच एवर इज मिनिमम। सो लेफ्ट मीन वैल ऑफ करंट ऑफ लेफ्ट, मतलब कॉम्प्लिकेटेड हो रहा है, इट कैन बी डन इन अ मच सिंपलर वे, बट जस्ट टू मेक थिंग्स मच क्लियरर फॉर यू, I'm just doing it like this. I would have just maintained global variables and done this, but yeah, like this will make things easier, right, when we write the second method. So min val current of left, current of right, max val भी सेम करते हैं, मतलब कुछ खास कॉम्प्लिकेटेड नहीं हो रहा, बस थोड़ा कंडीशंस आ रहा है, वो भी वी कुड हैव अवॉइडेड इफ वी डिड इट डिफरेंटली, बट अगेन लाइक दिस इज मच मोर मच बेटर एक्सप्लेन्ड देन इफ वी हैड डन द अदर वे, राइट। तो मैक्स वैल करंट ऑफ राइट, चलो, so we have taken the max of these two, but a subtree consistent only one difference is a binary tree, isn't it? It's a binary search tree, yes, it's a binary search tree, yes। so bool sorry, void find answer node star current and int target, so we have the target and we have the current given to us। now what we'll do, so we have computed all these mean value, max value, so we'll check if the current node is a binary search tree। so if first thing is if current of left equals to null and current of right equals to null, then it is a leaf node, so BST, it is a BST। now we'll check if current of data is equals to target, right, so answer equals to, definitely is the best possible thing, so answer equals to 1, just एक नोट लगेगा, and answer equals to 1, we'll just replace answer to be 1, and yeah, like we can just return after this, right, we can just return after this, और कुछ करना ही नहीं है, answer equals to 1, like if a single node value is equals to target itself and it is a leaf node as well, तो और कुछ करना ही नहीं है, else, चलो else करते हैं। else क्या करना है, मेरे को जानना है what if it is a BST, if it is a BST, right, bool let's make it bool. Why bool? Because it will also check. Why bool? Because it will also check if the subtree is a BST, right? It will return if the node itself is if the subtree itself is a BST, so it will return true for a single node, right? If it will return true for a single node, it is a BST. A single node is a BST, so it will be bool, right? Return true. So this single node is a BST. Else, let's go to the cases again. Else if current of left इज इक्वल्स टू नल, दैट इज हमारे पास बस राइट चाइल्ड है, लेफ्ट चाइल्ड है ही नहीं. करंट ऑफ लेफ्ट इज इक्वल्स टू नल. इन दैट केस बुल इज BST इज राइट BST equals to find answer current of right target. Now if is right BST and then the max value, the mean value of current of right is greater than current of data, that means the current node is a BST. That means current node is BST. So in this case we'll return true definitely because it is a BST. We'll return true, but we'll also try to update our answer. Answer equals to max min answer comma the size of the subtree. Oh, actually no. We have to check also if the sum subtree is equal, right? If sum subtree of current node is equals to target, in that case answer equals to what? Answer equals to mean of answer comma subtree size, whatever this is the subtree size. How do we get subtree size? हमारे पास available है subtree size of current, and we'll update the answer and we'll return true, else will return false. ये BST नहीं है, return false, right? चलो again let's go to the third condition. Else if current of right इक्वल्स टू नल. इसका मतलब क्या है? करंट ऑफ राइट इक्वल्स टू नल मतलब वी हैव द लेफ्ट चाइल्ड, वी डू नॉट हैव द राइट चाइल्ड. लेफ्ट चाइल्ड क्यों है? बिकॉज इफ लेफ्ट चाइल्ड वाज नॉट देयर दिस वुड हैव बीन सेटिस्फाइड बिफोर, राइट? तो लेफ्ट चाइल्ड है, राइट चाइल्ड नहीं है. तो विल जस्ट चेक बुल इज लेफ्ट BST इक्वल्स टू फाइंड आंसर करंट ऑफ लेफ्ट टारगेट. तो हमने फाइंड कर लिया इफ द लेफ्ट सबट्री इज BST, इफ is left BST and then max val of current of left is less than current of data, तब proper BST है. तो current node is BST. So we'll just write whatever is here, same thing. We'll just copy this. थोड़ा बड़ा हो रहा है बट ठीक है, सह लेते हैं. चलो दिस इज डन. इन ऑर्डर ही ट्रावर्सल कर रहे हैं, वही कर रहे हैं, बट देर इज ईजियर वे टू डू BST, राइट? बट इट्स नॉट जस्ट BST बट ऑल्सो वी हैव टू कंप्यूटेड दीज थिंग्स एज वेल. बट हाँ, BST का वट एवर इज द लॉजिक दैट यू यूज फॉर BST वही इन ऑर्डर ट्रावर्सल ही कर रहे हैं. वट एवर लॉजिक यू यूज टू डू BST दैट्स वॉट विल डू, राइट? So else if both of the nodes are present, so we'll check if both left and right is BST. So is left BST is equals to find answer current of left target. Bool is right BST equals to find answer current of right target. दोनों ही है. तो if is left BST and then is right BST, right भी BST है, and then mean value of current of left, current of right, mean value of current of right is greater than, mean value of current of right is greater than current of data, and then max value of current of left is less than current of data. तभी current node is BST. So in this case current node is BST. So we'll check here if subtree size equals to target, will return true, will return true, else return false, right? And DFS root, and finally we'll do we'll initialize answer to some big value, let's say int max, right? and we'll do find answer, root and target, and finally if answered equals to int max, return -1, else return answer. That should be it. Are these type of questions common in interviews? Generally they will never ask this complicated, like doing so many things together, but yeah, like each of them independently are common questions, together rarely, like unless it's a very like tough interview, they will never ask, like it takes a lot of time to implement, right? So generally they will avoid asking these questions, but yeah, like if it's independently, each of these concepts are very important when it comes to interviews. uh, Okay, time limit exceeded. How did we? Okay, we used an unordered map, right? What is the size that's there? 10 to the power 5. For 10 to the power 5, we are extending the time limit. That's interesting. Uh, let's maybe do unordered map. Not sure if that helps somehow, but yeah. This should have worked, but yeah, like not sure how the time limit has been set. Or maybe we are running into some infinite loop somewhere, not sure. Let's see. We are always doing left and right only, right? We are not even going to a null node, so that's there. And if current equals to null, just return. Here if current equals to null, return true. Just return true, right? Yeah, I think maybe that could have been it for another map. Let's see. We are getting the answer. Let's run this. Maybe there was some null node given to us and that would have, but that should not have given TLE. So now it's done. Okay, so this was the code for the last question. Again, like the code looks a bit complicated and scary, but eventually it's just like finding the sum of a subtree, finding the count number of nodes in a subtree, the minimum of the subtree, maximum of the subtree, and checking if the node is BST or not. Or in fact, like instead of finding minimum and maximum, you can just club entire logic together in a BST method that would like determine if the node is a BST or not BST, right? Why can't we check for sorted array for BST? Sorted array, think about it, why can't you check for sorted array? Complexity बहुत ज़्यादा हो जाएगा ना, you have to accumulate everything and you have to check if it's a sorted array and like that, so the complexity will be more. Anyways, that's how you would solve this. Again, like BST check करने का code will might be much simpler. Actually it is much simpler. You can just write this entire thing in like maybe 3-4 lines of code just to explain, like this code is much better explained itself. It's more explanatory than the other codes that I can write. You can just maintain two global variables, max and min, or class variables, and you can just like without having to maintain this min val and max val, you can easily solve. And you don't have to care about left is null, right is null, these many conditions, right? So that can be easily done. But yeah, like just to make things more clearer for you, I have done like this. You can feel free to do it in a much easier way, right? The time complexity and the space complexity, again, like it will be order of n, because we are using, when we were using a map, it was n log n because access time is log n, but here as we are using unordered map, it will be order of 1. So this is just doing a DFS, so order of n and again order of n. So the total time complexity will be order of n, space complexity will also be order of n. Okay, because we are just doing a DFS, nothing else. We just have a few conditional checks. Other than that, we are just doing a DFS. So there is nothing to add to the time or space complexity. Cool then. Thank you guys for joining in, and I hope that you enjoyed the session. You enjoyed the contest. So I'll be seeing you. I'll be seeing you in the next session on Sunday. So yeah, like good luck for the next interview series, and I'll be seeing you then.